In this example, I would like to find probabilities for a binomial distribution after verifying that the normal approximation to the binomial can be used, and then I'm going to use the normal distribution to find those probabilities. Now I could easily find these probabilities using technology for the binomial case, but covering the normal approximation to the binomial is important because in future examples it'll provide justification for confidence intervals for proportion and hypothesis test for proportion. Okay, so I have a binomial distribution with n is equal to 30 and p is equal to 0.6. I first want to verify that the normal approximation could be used in the first place. So in other words, I need to verify is n times p at least 5, and also is n times 1 minus p at least 5. So n is 30, p is 0.6. Is that at least 5? Well, 30 times 0.6 is 18. It's definitely at least 5, so that checks. Checking the other product here, I have 30 and 1 minus p. If p is 60, then the complement to that is 0.6 or 60%. The complement to that will be 0.4. Is that at least 5? Well, this product is 12, and that is also at least 5. So the conditions are met to use the normal approximation. My first one is finding the probability x is more than 10. It doesn't include the 10, so I have to keep that in mind when I'm applying the continuity correction. But before I do that, I'm going to need mu and sigma. Okay, the two parameters we need to find probabilities for the normal distribution are mu and sigma. If we were using the binomial distribution directly, the two parameters we would need are n and p. So in other words, I'm not putting n and p into my normal CDF in the calculator. It's expecting mu and sigma. So mu is n times p. Okay, so if we can use the normal approximation, mu is going to be equal to n times p, which is also the mean or the expected value for the binomial distribution. Plugging in the numbers, okay, we actually found that up here. That's going to be 18. And the standard deviation, remember, is the square root of the variance. The variance for the binomial distribution is n times p times 1 minus p. So that's going to be the square root of n times p times 1 minus p. Some textbooks call 1 minus p q. They use the letter q to represent the complement to p. So plugging in the numbers, I have 30 times 0.6 times 0.4. I'm getting a little messy here. My apologies. So getting my calculator out for that, finding the square root of 30 times 0.6 times 0.4. All right, I get that value, and I want to carry it out 4 decimal places just to get the best possible approximation I can. I get 2.6833. All right, so now I have my two parameters that I need to use the normal cumulative distribution function in my calculator. So going back to part A, finding the probability that x is greater than 10, I have to apply the continuity correction and recognize the fact that I am not including the 10. So I'm going to be adding 0.5 to that. If you need a review, my previous example I just did examples of applying the continuity correction. You're certainly welcome to take a look at that. All right, so my mean is 18 for the normal distribution. 10.5 is below the mean. And I have a greater than situation, so I'm shading to the right. So this is not standard normal. If you were to use your Z table or the standard normal table to find the corresponding probability, you would have to convert 10.5 to a Z-score by subtracting the mean and dividing that difference by the standard deviation. Okay, but I want to save a little bit of steps, so I'm going to use my calculator directly. Oops. Okay, so I'm going to go to my normal CDF, which is in the distribution menu. My lower bound is 10.5. My upper bound is an extremely large number, theoretically positive infinity, but just put a 1 with a bunch of zeros. I need to change my mean to 18, and I could put in 2.6833. That's fine. One thing that's cool about the calculator is that if you are feeling particularly lazy, you don't have to find this first. You can literally put in 30 times 0.6 times 0.4 underneath that square root here. And then enter and enter again. So rounded to 4 decimal places, that's 0.9974. Okay, so a huge chunk of this curve has been shaded. Okay, almost all of it, so I didn't sketch it proportionally correct. So part B, I want to find the probability x is less than or equal to 22. Okay, that's also going to be a fairly high probability. All right, so probability x is less than or equal to 22. This includes the 22. So after applying the continuity correction, so I can use the normal distribution, this is going to be the probability x is less than 22.5. Okay, so the number 22 goes from 21.5 up to 22.5. So I need to go all the way up to 22.5, and I want the area to the left of that. Again, shading a bell curve, putting the mean in the middle, which was n times p. 22.5 is above the mean, and I'm shading to the left. Going back to my calculator and going back to the distribution, the normal distribution. Selecting option 2. My lower bound now is going to be -1 with a bunch of zeros. My upper value is 22.5 because I'm stopping at 22.5. And I can leave mu and sigma alone. And rounding to 4 decimal places, I get 0.9532. Okay, now this is not the exact probability, it's an approximation. If you wanted to find the exact probability for this, or as close to as exact as we can get using technology, we can go to the binomial distribution and just see how that compares. Okay, so I want to do that really quick. So going back to my distribution menu, and then I need to select binomial CDF. I want the cumulative function because I'm finding an area, or I'm sorry, I'm finding the sum of the probabilities from x is equal to 0 up to x is equal to 22. Okay, so the number of trials is n, which is 30. The probability of success is 0.6. And my x value where I'm stopping, the summation is 22. All right, so comparing these two probabilities, here's the probability using the binomial distribution. Okay, rounding to 4 decimal places, that's 0.9565. When we use the normal approximation, we got 0.9532. Okay, these are pretty close together, okay, but they're not exact. That's why this is called an approximation to the binomial. Last but not least, I want to find the probability that x falls between 5 and 10, inclusive. Okay, so the probability x falls between 5 and 10, inclusive. I need to apply the continuity correction going from binomial to normal. I'm including the 5 and I'm including the 10. So 5 actually starts in the continuous case at 4.5 and 10 will actually stop at 10.5. Okay? So it's important to take your time with this step. Okay? I know this section, if you're taking my class, can be a little confusing. That's why I made a separate video example for just this part. All right, so drawing the bell curve, putting mu in the middle, which was 18. I'm trying to make this a little bigger. Now both 4.5 and 10.5 are below the mean. Okay, so I will shade my area that represents that probability statement. So that gives me what my lower bound is and what my upper bound is. Going back to the normal or the normal CDF, changing my lower bound to 4.5 and my upper bound to 10.5. And I have mu, which is 18, and sigma, I'll just go ahead and use the decimal approximation, was 2.6833. Again, I could have actually put in the square root of n times p times 1 minus p here. And then enter and enter again. All right, so I clearly did not draw this proportionally correct, okay? Okay, so this is not 0.2 amount of, or percent of the shaded area, okay? I tend to draw these larger, the areas larger, so that I can see the values on the horizontal axis. All right, and if you wanted to do the binomial distribution for comparison, we'd actually have to do this twice. We would have to find the cumulative area, or sorry, the cumulative probabilities up to 10 and subtract out the cumulative probabilities up to 4. Since we're including the 5, the area that we want to subtract out is from 4 to 0. So I'm going to just compare that briefly and do that just to show you that we're going to get an approximation, or how close the approximation is. So 30.6, stopping at 10, and then I'm going to subtract out the sum of the probabilities I don't want. And that was from 3 down to 0. All right, so you see that when I use the binomial distribution and compare it to the normal approximation, they're actually pretty close. Okay, so rounding to 3 decimal places, these both would be 3. But if you're taking my class, this section that we're covering, all of the homework problems are going to be emphasizing using the normal approximation to the binomial.